Дорогие товарищи, мы начинаем новый семестр, и в этом году у нас предстоят некоторые большие мероприятия. Это в первой неделе июня будет наш 10-й юбилейная международная конференция в Дивноморске, и она будет посвящена 90-летию создания кафедры теории вероятностей. Вот сейчас я единственное, что только это хочу сказать. Также я еще раз и передайте всем остальным своим друзьям, что мы желаем слышать не только доклады участников, не только то, что они сделали вчера, но и большие обзорные доклады. Вот как сегодня мы будем слушать обзорный доклад по контактным процессам. Так что, Елена Борисовна, давайте начинайте.
Альберт Николаевич, I try to translate, and Professor Chen, with great pleasure, we start our seminar with your talk. And firstly, Professor Shiryaev said us about the conference in Dimnomorsk in July, and I think all our participants, yes, in June, yeah, and all our participants can take in this conference in Divnomorsk, and if you have possibility, Professor Chen, of course, was invited by Professor Shiryaev. Now you can start.
Минутку, Лена. Professor Chen, you remember, of course, that we had some times ago discussions about the possibility of the China's releasing this conference in Divnomorsk, and we confirm this invitation, and you will have the corresponding information a little bit later about this conference. Lena, начинайте.
Professor Chen, you can start your talk. You have 1 hour, please.
Yes. First of all, I'd like to thank you for the opportunity to present this talk in your prestigious seminar, which is a great honor for me. And then firstly, answer the question Professor Shiryaev asked. We will carefully consider the time plan, and we will certainly very well join your conference in this summer once we know the exact schedule. Yeah, we have to check the time schedule. Before my talk, I'd like to congratulate you again for the 270th anniversary of Moscow State University. And I was in Moscow 3 weeks ago with a delegate from my university. And you see, it's 10 people from my university. And I was in the bigger events in Kremlin. Also, I met Professor Professor Chen to discuss the possible cooperations. Let me recall the facts that the great ties between my university with Moscow State University. In 1952, the Department of Mathematics at my university was reorganized as the Department of Mathematics and Mechanics in light of the so Moscow State pattern. And the group of probability and statistics was set up in 1956 at Peking University in advice from Russian experts. And the two young faculty members, Jiang Zhepei and Wang Zhikun, were sent to Moscow State University to study with Professor Yagorun and Dobrushin from 1955 to 1958. Of course, the advisor formally is Professor Komgrov. And Professor Dinkin came to visit us in 1957, which was a big event in probability circle in China. And in 1950, many Russian textbooks were introduced. And actually, the book I mentioned here is a reprint of this tradition. And here is the article Jiang Zhepei wrote when he was in Moscow State University. You see, its time is 1957, which is almost 70 years ago. And now, with your help, the two portraits many portraits, actually exactly the 1+5. Komgrov, the portrait of Komgrov now is hanging in our corridors with other 5 Russian mathematicians. So now let me begin my talk. The subject of my research field is so-called interacting particle systems. And here's the monograph on this subject. And I quote from the preface of this book. It says, much of the original impetus came from work of Spitzer in United States and Dobrushin in Soviet Union. So interacting particle systems really originate from Russia in early 70s. And I showed this picture once I was in Moscow in last November. This was the picture I took when I met Professor Dobrushin in 1989 in Madison, United States. I also first came to Moscow in 1999 with Professor Minlos. So my talk will be divided into 3 parts: the basic facts of the contact process and new developments of the contact process, and finally I will report our contributions in this subject. So first part is the basic fact of contact process, because this probably is not very familiar with you. And this is a probability model to modeling the spread of disease, like the COVID-19 we just had a few years ago. And this is the one of the basic models of interacting particle systems, and a good property is there is phase transition, which makes this model interesting, and it's related to population, which is also the population now is a popular topic in probability. So think about the disease transmit among individuals or the fire. spread out in a forest. So, well, let's think about the graph. It's the forest or a set of individuals, and a vertex of the graph can be thought as a tree or individual person. And there are two possibilities of each individual, either healthy or infected. And now let's fix the notation. So the graph we call the underlying space, and vertex we now call the site. And if it's the state is 0, we now call there's no particles. If the state is 1, we call there is a particle. So we think about a particle on the graph, and the collection of the states is called configurations. And all the possible configuration is our state space. So the state space is a product of 0, 1. And each individual will evolve as time goes. So either is health from 0 to 1 or to 1 from 1 to 0. So that means either health and changes states from health to the infected or infected to the health. Individually, the states are very simple, 0 or 1. But the trouble is this transition is not Markovian. And collectively, the whole set, all possible states is Markovian, but not simple because there are many individuals. And let's make the transition mechanism very simple. From 1 to 0, if someone is in fact, he will recover after exponential time, and simply he will recover from the bad state. And if he is healthy, he could be infected if there is a neighbor, infected neighbors. And here is only the interesting mechanism. So the waiting time now is exponential, and the mean of waiting time is proportional to the infected neighbors. So if there's more neighbors infected, he's going to quickly get infected. Otherwise, he can stay for a longer time in health state. So let me introduce the only parameter in this model, the lambda. So the mean of waiting time from health to infected is proportional to the number of infected neighbors divided by the lambda. So if the lambda is larger, it's more likely to get infected. So here is the construction to this model. So this is done by Harris. So this shows this model exactly exists. We can construct this model by some independent Poisson flows. So each arrow means there is a transition of the infection occurred. So let me show this picture. So this is a picture. Suppose there are some Poisson flows already given. And at the beginning, this one was infected. So he's going to infect the neighbors. And now the neighbor is sick, and neighbor keep going and infect other neighbors. So in this sense, you can say the disease spread out among neighbors. And this cross means that this individual recovered from infection. And now we we look at the behavior of all individuals. So we look at all the states of the sites, and equivalently, you can just look at the set. All the sites are infected. So these two notations are equivalent. One is all possible states, all states of the individuals. Otherwise, we just look at the set which are infected. And let's agree, these are the initial states, and that's the state at time t. So if you look at a set, right, this is all the infected individuals at time t. And this model is very simple. So once the set hits the empty set, this means there's no infected people. Everyone is healthy. Then from that time on, everyone is healthy. So this is a trap, and the evolution will stop. And if the graph is finite, if there's only finite graph, then we can think for seconds we could realize this state will eventually, all the individual will recover from infection. So everyone is healthy and the disease disappears. For this reason, usually we will consider infinite graph, because otherwise the story is stopped. It's eventually everyone recovered. So usually we just take the Euclidean lattice. And another observation, if at the beginning there are infinite many individuals infected, then after any time, there are always someone get infected. So this will never be empty. On the other hand, if at the beginning there are only finite number of individuals get infected, then the probability that infection will the probability that there is infection will decrease, because as we mentioned before, once everyone is healthy, once H is empty, then the process finished. So because of this observation, we will treat the two cases separately, either begin with finite states or begin with infinite. This is just two totally different phenomena we will treat separately. And let's begin with think about there's infinite graph and there is finite. The initial state is finite. This means there are only finite infected individuals or insights, or finite number of ones. As we mentioned, this probability, there is still infection. The probability is going down, and is monotone in lambda. That's obvious, because the larger lambda, the more likely this set is going to, there's more infections. So we can imagine rho will eventually either be 0 or positive. That's of course related to the initial state, but a careful analysis shows this. If we consider the so-called critical value, the lambda c is the minimum lambda, makes the limit positive. We define this as a critical value. This only depends on the graph, and it has nothing to do with initial state A naught. We will call this critical value. This means if lambda bigger than lambda c, then there is always disease. If lambda less than lambda c, less than critical value, then eventually the disease will disappear. So that's this is called the phase transition, and this makes the model interesting. And we like to know what's the critical value. And another question is rho lambda continuous in lambda? And the very embarrassing, we don't know too much. We only know there is the lambda c is non-trivial for a Euclidean space like ZD. And for the first dimensional, we know estimates 1.5 and between 1.5 and 2. And some simulation indicates the lambda c is very close to the square root of E. That's just for one dimension. And we don't know too much about high dimensional. And for the continuity of rho lambda, the answer is true, yes. The answer is yes for only one dimensional. And this was done by Professor Grimmett of England. And for this marvelous work, he got a position in Cambridge. You know, Professor Grimmett got the position because of this work. He shows the continuity for one-dimensional contact process. And now let's talk about the infinite case. If for the infinite case, there are infinite many individuals sick at the beginning. And let's take this two extreme. That's all individuals are healthy, and one means everyone is infected. For these two extreme cases, consider the distribution starting from R1 and after time t. And after second thought, you will say this actually is monotone in some sense. Mu t is decreasing as time goes. So the number of individuals get affected getting less and less. So there is limits. So in some sense, this limits starting from 1 is the so-called largest invariant measure. And the question is, are they same? Is that the limit, upper limit, will eventually become vacant everywhere? And again, this brings another critical value. That's for larger lambda, this could be different. And for small lambda, this could be same. And that again, this is a critical value. And this critical value or critical phenomena appears in many models of statistics. And for us, for the counterpart, because this relation of dualities, you see this side, it's about finite case, and that's the infinite case. These two are equivalent, are same, and this give us the identity, the two critical value actually are the same. So in this sense, the good news, although we introduce two different definitions, but they are exactly the same, and we can solve one question and answer two questions. So one and get the answer for two questions. And there is once, so it's clear if it's subcritical, namely lambda less than lambda c, it's relatively trivial because there are only one infinity invariant measure. And if it's bigger, in a supercritical case, let's make it interesting. And there are two different invariant measure, and all possible invariant measure are linear combination of these two extremes. So this gives us a very clear picture how the infinity looks like. And here's a picture that shows what we mean. This indicates that if you begin with finite states, I use this notation to indicate it's a finite state, then this finite state will roughly grows linearly. So at some fixed set and is proportional to some proportion as time goes. So it grows linearly. And among this region, the distribution looks like the invariant measure. So although we don't know the exact critical value, but we know very well about the limit behavior. In that sense, we're happy with the results. And for the classical model, let me mention that we construct the classical process by Poisson flows, and the Poisson flows can be a limit of some exponential distributions. So in this sense, contact process can be related to oriented bounded population. So you may think of this as bounded population, and if we know some knowledge of population, we can derive the same results for bounded population. Actually, for the continuity of rho, it is actually done by bounded population. And there are many work about the population, and I won't get too much involved. I mentioned the book by Grimmett. This is the main reference of population. And again, for population, there is a critical value, the PC, and there are also phase transition. And in this sense, the two models are intimately related. That's so much for the traditional results about the model, the basic knowledge about the model. And around the 1990s, more or less, that's all we know about. And we still cannot find the critical value, and we cannot prove the continuity of the survival probability. So people are looking for the new directions. In last decade of the 20th century, people's attention was addressed to the tree. So you see, in 1992, Pimentel wrote a paper called the contact process on trees. This begins a new phase of the new period of study. At the same time, I also noticed that we should look at the tree. I consider the finite nearest particle system on tree. Please be aware, at that time, there's no exchange between China and the United States, because at that time we don't have email, and we cannot know too much. We get the annual probability probably 2 years after. So I think everyone did it independently. And Shrem, Benjamin Shrem of Israel, consider population on tree. So you see at that time, people begin to consider interacting particle systems on tree. And one interesting phenomena is for counterfacts on tree, on regular tree, there are 2 critical points instead of just 1. So now we will have 2 critical points. One is what we discussed before. Above this number, there are non-trivial invariant measure. And interesting enough, on tree, between this period, these intervals, between lambda 1 and lambda 2, there are infinitely many extreme invariant measures. And if lambda getting bigger, then 2 extreme invariant measures. So this is what we observed on ZD. There are only 2 extreme invariant. We mentioned a linear combination of 2 invariant measures. And that's the new phenomena. And for each case, we try to identify when is this the case. So for regular tree, we have good answer. And in general, it's still unknown to us. I think it's still wide open. What's the sufficient and necessary condition for the 2 critical value are really different. Namely, this case will happen. We know it's happen on tree, and we know it will happen on Galton-Watson tree. But for general, there's good conjecture. The exponential growth of the volume. But in general, we really don't have answer. We know it only case by case, some examples. And we know in general, we do not know in general. So that's a big question. And we still don't know. And then let me mention another simple fact. That's another observation made by Dayue. I said before, if they are only if the graph is finite, then in some sense it's trivial, because if you run a contact process on these finite intervals, eventually everyone will get recovered, and there's no disease, everyone is healthy. So this means the disease disappeared. And because the state is finite, so this will occur almost surely. In this sense, people do not pay attention to finite intervals. But the rich person noticed an interesting phenomenon that if it's subcritical, this mean is roughly log n. The n is the length of the interval. And if it's supercritical, then the mean is about e to the n. So these two behave quite differently. One is about log n, one is about e to the n. So even it's finite and will eventually disappear, but they are really different because the one is supercritical, one is subcritical. I mentioned this later, I just mentioned. Actually, Dayue wrote 3 papers to finish the 3 statements. And he first showed this by one paper, and he showed another, he wrote another paper with another co-authors to show. And the critical case is usually most difficult, and there's no good knowledge. We only know it grows not too fast. That's an interesting observation which relate to our work. So that's the some new developments. And now let me come to the third part, our contributions. During the last from 1990s, many of my students study the content process. So here's the thesis for master's degree and dissertations for PhD. And if you look at the names, all relate to the content process. For Galton-Watson tree, for regulatory tree, and on homogeneous graph, and so on. So you see, all they relate to graph. And although this name is nothing to do with the content process, actually, it is content process. So our group had some discovery on the content process. And I myself wrote papers with my students on this subject. That's one is content process on scale-free networks. And another one is content process on the regular tree with random vertex weights. So both are random graph, but one is random tree. We call it a scale-free network. One is regular tree, but with random weights. And we got the similar results. So let me talk about the first paper, the content process on scale-free networks. And here's the idea about the scale-free network. Suppose there are n vertices, and we assign each vertex a weight. So that's Wi is the weight of this set I. So I is run from 1 to n. And that's the probability assigned to the edge between I and j. So take this as the weight, and this probability will with this probability, there is a connection. There's edge. Otherwise, this edge won't show up. So this is called the configuration model. That's not by me. It's by Chen and Lu. So this is a way to produce a random graph. So once we have the mechanism to generate the random graph, there are some property, namely the degree of the graph, degree of vertex will follow so-called power law. So the number have has the vertex we chosen has degree k is proportional to k to the minus beta. This is so-called scale free, because when you eventually will increase n to infinity, and the proportion, the distribution will keep the same. So this is called scale-free random graph. And also there's a property called small world, namely the diameter of largest components. We cannot make sure, we cannot guarantee this is connected. So there is the largest components, and the diameter of these components roughly log n. So although the size is proportional to n, but the distance of between 2 points are not too far away. Now we choose the largest connect components and fix a vertex to run the root, and then we run the contact process in the root. So now we have a random graph and of size n. Actually, it's less than n. And we start a contact process from 1 point, and we wait to see when either the disease will transmit to neighbors, or at some point they will disappear. So the transition mechanism is the same on the scale-free. So now this is a finite graph, and this means, well, because it's finite, so we use the set notation. So one site is removed at root 1 because this individual now recovered unconditionally, they were, and one gets infected because a new site is added because infection. So this rate is lambda times the neighbor of infected people. So there's a two, either increased by one, added one site, or remove one site. That's the what we have now. We have a finite model on the random graph. And now we also can define critical value, lambda c. As I mentioned, what the work by the rate. Now we just look at the how long the system, the contact process will get to the extinction. So that's the time this disease disappear from the random tree, and that's how long we wait. It's random. It's random, and we wait either how, if there is sigma n, the disease will last exponential time. This age is constant for some positive gamma. So if there is positive probability the contact process lasts for this large time before extinction, then we will say supercritical. Otherwise, we say it's subcritical. So that's if you look at the results of the rate, this is a natural formulation of survival for the finite system. And we introduce the critical value for this finite model. And we got some results on the random graph. Namely, this depends on beta. For this model, the beta is somehow between 2 and 3 is interesting case, and we use the results of others to study the counting process for the scale-free graph. And our conclusion is, if lambda is positive but very far away from 1, and beta, this is the power of degree distribution of power law. And for sufficient large n, there is a large component, and we run the contact process on this large component. Then this disease will last a very long time with positive probability. So this means for any lambda, there's always positive probability the counter process will last for the exponential time that's epidemic with positive probability. In other words, we show the critical point lambda c is 0. That's one of our results. And for the case beta equals 3, the statement of results is same, but the estimate of lower bound is slightly different. It's like this, which is different from the previous one. That was the lower bound, but the conclusion is same. The critical value of this model is 0. As long as lambda is positive, this will survive for large time. That's the main results of one of my paper. And let me just mention that we need some preparation for the proof. Namely, we need the knowledge about the random graph, and that means the two components of the random graph, there is good chance they will intersect, and as long as the volume is large enough. And another result is the two disjoint subsets. If the volume is large, then the distance cannot be too far. Although they are separated, but you see, the distance larger than 1 is bounded above by some number. So with very large probability, they are just one step away. That's the about the random graph. And here's another the estimates of the giant, the connect subcomponent, and which is the size about square root n. So with this the supports, we need another another result called the so-called star lemma. Namely, if there's one infection and there are many neighbors, then this will transmit to the neighbors in certain probability. So the time will be, in fact, with this bound, the neighbor will get infection. So with this preparation, we are able to estimate the transition of disease and get the statement. For these two cases, we know that the critical value is 0. That's what I like to report. And the last part is based on these 4 papers. And I like to conclude my talk with the 2 news. So your colleague, Professor Zakharov, was here last year, and he got an award from our president. And also, the professor, our president, went to Moscow to award the honorary degree to Professor Sadonevich. And there is an institute called the Russian Mathematical Center in our school to promote cooperation between 2 great nations. And this is a gest that anyone who are interested in this interchange can contact this center, or you may write to me. Thank you very much for your attention. I finish my talk.
Thank you, Professor Chen, for your very important for us for such talk. Thank you. Dear colleagues, please your questions, comments. Maybe some questions, please.
No, there's no voice.
Do you
Альберт
hear
Николаевич
me?
хочет спросить, но его не слышно.
One moment. We have a question from Professor Shiryaev, but he has some problems with... Альберт Николаевич, слышите нас? Алло, Альберт Николаевич, звук выключен.
Вот, включен.
Все, отлично, теперь слышим.
Теперь слышно?
Да.
Professor Chen already mentioned something about statistical physics. I'm interested about the work. Does exist works about the connections between contact processes and typical system of systems of statistical physics, where moving of the particle defined by Hamiltonian system and so on.
Yes. Well, of course, this is a very simple model. It's a toy model. There's no Hamiltonian on this counter process. For the stochastic Ising model, then actually that's probably the first work by Dobrushin. There is a Hamiltonian, which is more complicated, more interesting, and I only know little about. So for the
I
contact process, there are no reversibilities.
No, by the way, you mentioned, you shown the pictures, your with mean loss. And recently in Russia, the following books, small books, Introduction to the Mathematical Physics was published. I think that even Russia, many Russian people don't know about this one. But in any case, I think that if we want to understand connections of the contact processes and some simple results of the statistical physics, look this book.
This is by Professor Minlos?
Yes, it's book of Professor Minlos.
I see. Thank you. I didn't know.
It appears in how to say, recent in Russian. Так, Лена, еще вопросы какие? Задавайте.
Please, colleagues, do you have some questions? I would like to speak some words because we consider branching random walks all multidimensional lattices. And by my opinion, this work is very interesting because you consider the interaction of particles. We, for example, we discover such effects as bifurcation, phase transition on something else, supercritical, critical, subcritical processes, and how to say, more detailed classification in situation, but we didn't consider interactions. But by my opinion, it's very, you told us that you consider toy models, but I think in a frame of such toy models, the questions is very difficult. And maybe I know only one work by Kalinkin. It was published in the beginning, I think 20 years ago, and he considered some models with interactions. It's, I think it's very difficult.
Нет больше вопросов.
Maybe some comments, dear colleagues.
Ну, у нас Ульянов специалист по Китаю.
Альберт Николаевич, я не, даже если бы я был специалистом по Китаю, китайских математиков настолько много, и их интересы настолько широки, что я должен обладать какими-нибудь энциклопедическими знаниями. But okay, I have some question about Professor Chen. As far as I remember, there are models, graph models, where the disease is considered, and the how to say, the limit of not the limit, but there are some estimates for eigenvalues of matrices, corresponding matrices, and the maximum eigenvalue is connected with rate of extension of disease. And this is estimated by number of circles of random graph, number of circles. So my question is, maybe there are some other problems where the number of circles are interesting. Number of circles in graph, I mean number of triangles, rectangles, and so on.
Well, you mentioned the largest eigenvalue of the model for some quantities, and in another model which I studied, it's I mentioned the nearest neighbor model, which is reversible. Then this quantity relate to the convergence of the how fast the distribution will converge to invariant measure, and that's what the only case I met with the largest eigenvalue. At some point, it's also very interesting to us because we want to show the exponential convergence of distribution to the invariant measure. But sorry, I do not fully understand your question. So probably we are talking about
maybe I repeat my question. So in another way, so is it important in your research to consider number of circles in random graph? So I mean number of triangles, number of rectangles, and so on. It doesn't matter.
For this model, for content model, probably we do not need this quantity because we only need the nearest neighbors. So the number of circles somehow is more involved. See, if we are look for the behavior for larger time, because if you think about the disease transmit along the circle, then this will bring another features. I do not know. For now, I don't know. My answer is I do not know, but I will look at carefully.
Okay.
Thank you.
Thank you very much. Thank you.
And I have one question. Could you explain in such model the influence of dimension of space? How this the result?
Well, first of all, if the larger the space, then there's more chance, more likely the disease will survive. So if you can embed one space into another one, we have the estimates about the critical value. We can use a coupling to couple two models. In this sense, the larger the space, the critical value is getting smaller. That's easy. And so for dimension, you mentioned dimension, the higher dimension, the critical value is getting smaller. And somehow, if the dimension is greater than 19, the continuity of I mentioned the survival probability rho, that we still don't know continuity of the rho, the survival probability for dimension between 2 and 18. We know for dimension 1, I mentioned the Grimm's work, and by others' work, that it's continual for dimension greater than 19. So in higher space, there's some easy, it's become easier, and we can get useful results. But I don't know what happened between dimension 2 and 18.
So it's, as I understand, it is open question, yeah?
Yes, a lot of open questions. Basic questions are unknown.
Yeah. So thank you very much for your comments.
Lena, maybe one more. Lena, maybe one more short question.
Please,
Professor Chen, maybe one more short question now not about your talk, but about Sino-Russian Mathematical Center. So, because this is rare possibility to ask you directly what's happening. So, do you know some events which are planning in Russia this year or in Moscow in the frame of?
Oh, actually, I just got an email from Professor, the vice chair for foreign events, and he asked me about the summer school of 4 universities in which Moscow State University and the Peking University are involved. So that's one we are thinking about now, and of course that's for graduate students, and for conference for the academic events, I think it's up to individual professors to think about, to plan, and since we have the conference, multidisciplinary mathematical conference, which happened held in Beijing in 2023, and last year in Moscow. So very likely we will have a similar conference in Beijing this year. And I understand Professor Valabaya will come to Beijing in March.
No. Excuse me, please. Not in Beijing. Professor Ulyanov. Volodya.
Oh.
It's a little bit mistake because it only planned now the conference not in Beijing this much. It will be a conference from 17 to 23 of March. Володя, скажи, пожалуйста, где будет конференция? Планируется.
Shenzhen.
In Shenzhen, not Beijing, in Shenzhen. Yeah.
I see. Okay.
So
Now I want to say the following. Professor Chen, you have very big scientific position in China, and so please inform your colleagues about our seminar today, which we have had today. And also, for us, it will be interesting to know about China's seminars of the following type. I think that many your seminars are going in English also, yes. And so it would be very pleasant for us if we shall have such possibility to attend to present on your seminars. Thank you.
Sure. Well, we will, from the Russian Center, we will announce our events on our website.
Professor Chen, thank you once more, and we hope in future for useful discussions in such the direct of your topic with when we consider the system of particles with interaction and something else. I hope we will be in contact, and once more thank you for your talk.
Thank you very much for your time, and keep in touch. Спасибо.
We will sometimes our foreign participants give their talk in English because we have mainly the Russian auditorium, Russian participants. Our Russian participants of the seminar give their talk in Russian, but we will inform about the program of this seminar, and I hope it will be interesting when we will include our speaker from English who who gives their talk in English. So we will please join us for such
But
talks.
very often we have people from different countries and they are speaking in English.
Now,
Yeah, yeah. I have used the seminar site, so I can revisit your site next Wednesday.
next, I would like to announce the program on the next Wednesday. It will be talk of Andrei Lyulintsev from St. Petersburg Mathematical Institute, Yakobev branching random walks, connecting with orthogonal polynomials with discrete time. Please join us, but this talk will be in Russian. Я еще раз повторю название. Значит, будет выступать Андрей Люлинцев, Якобиева ветвящееся случайное блуждание, соответствующее ортогональным многочленам дискретной переменной. Доклад будет, ну, на мой взгляд, уже завершающий фрагмент его диссертации. Пожалуйста, присоединяйтесь. Professor Chen, thank you once more. And now we finish our seminar. Thank you.
Thank you. Bye-bye. Спасибо.
Bye.